Fructose is a ketohexose. That means it is having a keto group and it is a hexose. Hexa means 6 carbons. 1, 2, 3, 4, 5, 6. Along with 6 carbons, you are having a keto group. What is the difference between aldehyde and ketone? Aldehyde group is having a C double bond O and a hydrogen, and it will be in the terminal. Whereas if you take ketone, ketone is having C double bond O and it will have 2 alkyl groups on 2 sides. That is called as ketone. So ketohexose, that means it is having a keto group and it is having 6 carbons and it is a polyhydroxy compound and it is a glucose. So this is called as ketohexose, or generally we will call it as fructose. Penultimate carbon, this is the terminal carbon and this is penultimate carbon. One carbon before the end carbon is called as penultimate carbon. This penultimate carbon, it is having a hydroxyl group on the right side, so we will call it as capital D. If it is on the left side, we will call it as capital N. So this is a D-fructose and it is a white crystalline. It is a white crystalline solid. Its melting point is 120 degrees Celsius. It is soluble in water as it is having plus minus charges and hydrogen bonds. Because OH, this will act as a water. So there are so many factors which will make this compound to get dissolved into the water. So it is soluble in water, and on the other hand it is not soluble in the ether and benzene like organic solvents. That means if it is having ionic nature and hydrogen bonding, then only it will be soluble in water. And it is the sweetest material of all carbohydrates. Almost all, it is a sweetest material, and when you taste it, it will be sweeter. And on the next point is, it is a levorotatory. What we have seen, when a plane polarized light is passed to the compound, that compound will make the light to turn toward the left hand side or right hand side. That is only called as optically active. If it turns toward the right hand side, we will call it as dextro, and it is denoted with plus sign. And if it turns toward the left hand side, then we will call it as levorotatory, and we will denote with a minus charge. So we can say that this compound is a levorotatory. We can say D minus fructose. That means it turns the plane polarized light towards the left hand side. Glucose is a dextrorotatory, fructose is a levorotatory. And it is the monomer inulin. Inulin is a compound which is made of fructoses. When fructose molecules they combine together, they will become a big polymer. This polymer is nothing but inulin. So inulin is made of monomers like fructose, or when fructose monomers combine, we will get inulin. And it is available in honey and fruits. Just now I said it is very sweetest material. If you taste honey, it will be sweeter. Why it is sweeter? Because it is due to fructose. Similarly, when you see smell of the fruits, you will see a sweet odor. This is due to the presence of fructose in the fruits. Now let us go into glucose. Like glucose, fructose also shows mutarotation. What is mutarotation? When a plane polarized light turns toward the left or right, we will call it as optically active. These optical active compounds, they will have a specific rotation. This rotation may change when put into the water. So change in specific rotation of the compound is called as mutarotation. Levorotatory is negative. That means it turns the plane polarized light towards the left hand side. It is a sign only, it is not a mathematical sign. It shows that it is turning towards the left hand side. This alpha and beta fructoses, they are different. When they are crystallized from different temperature and different solution, they will have a specific rotation different. So these are optical isomers. The compounds which are having everything same, only the difference is in rotation of plane polarized light, such compounds are called as optical isomers. So alpha fructose and beta fructose, these two are optical isomers. So alpha fructose shows a specific rotation of -21 and the beta fructose will have a specific rotation -33. When these two compounds they are kept in water, they will, in the solution of water, what will happen? Slowly this minus 121 also turns to minus 92, and beta fructose minus 133 also slowly gets to minus 92. So there is a change in specific rotation of compound in water with time. So this change in specific rotation is called as Newton rotation. Let us get into the chemical properties of fructose. Fructose molecule we have seen, again I will show you. Fructose, it is having a primary alcohol on the terminal sides. Two terminals you are having a CH2OH and you are having a keto group, and third carbon, fourth carbon, fifth carbon they are having hydroxyls, and this hydroxyl, third carbon hydroxyl is on the second, on the left hand side like glucose only. Only difference is in glucose here you will find a carbonyl group, and in fructose in second position you will get a keto group. You try to open that. So first concept is acetylation. These chemical reactions were done when the structure of the molecule was not known. Basing on the chemical reactions, they have drawn some conclusions. Using those conclusions, they have given the structure of fructose. As we already know this structure, I am trying to explain using the structure. Let us see acetylation. Acetylation is nothing but an introduction of group of acetyl. Acetyl group is nothing but CH3, C double bond O. This moiety is called as acetyl, and we can show with a short form as AC. So this is acetic anhydride. How acetic anhydride form? CH3, C double bond O, OH, it is acetic acid. When you take two acetic acid molecules and remove water, you will get acetic anhydride. So this acetic anhydride can be shown as ACOC. That means AC indicates for CH3, C double bond O, OH. And this acetyl group will replace the primary. In a hydroxyl group, you will have a hydrogen. This hydrogen will react with the rest of the part of the acetyl group and forms acetic acid, and this acetyl moiety will come and sit on the oxygen. You can find such hydroxyl groups 1, 2, 3 and 4 and 5. There are 5 hydroxyl groups in it. So if you take 1 mole of fructose, it requires 5 mole of acetic anhydride, and you will get a pentacetyl derivative. That means first hydrogen, second hydrogen, third hydrogen, fourth hydrogen, fifth hydrogen. These hydrogens are replaced by acetyl group. So you can see here, you can see first hydrogen is replaced by acetyl. C double bond O is as it is, and in second hydroxyl also, this hydroxyl which is on the left hand side also acetyl. Then fourth, fifth and sixth, all you are getting acetyl group. So this is pentacetyl fructose. So this pentacetyl fructose indicates that there are 5 hydroxyl groups in fructose. Then only it can react with 5 moles of acetic anhydride, and this acetyl group will be replaced in 5 hydroxyls. So we can draw a conclusion with the reaction that 5 hydroxyl groups are present in the fructose. Now I will tell you how to write in examination. In examination, they will ask you to explain the open chain structure of fructose. So what we are supposed to write, the acetylation, when you do the heading, you write that fructose molecule is taken, subjected to acetylation with acetic anhydride. Acetic anhydride will have an acetyl group. These acetyl group replace 5 moles of acetyl group is required for 1 mole of fructose. That means you are getting a pentacetyl fructose. This pentacetyl fructose indicates there are 5 hydroxyl groups present in the fructose. Same thing, only thing the difference is, if you don't know the structure, we will take the fructose and we will subject it to acetylation. We are getting a pentacetyl derivative. As we are getting pentacetyl derivative, we will draw a conclusion that 5 hydroxyl groups are present. And after that, you can write this equation using this formula. Then you will get good things. Now let us go into second question. Hemiester is nothing but any group, CHO group, a carbon linked to different alkyl groups, and it is having 1 hydroxyl group. This hydroxyl group reacts with methanol in presence of hydrochloric acid. When it reacts with methanol, this methyl will be replaced with the hydrogen, and this hydrogen and OH, they will come to hydrogen water. So methylation of oxygen is taking place in hemiacetal and it will be converted into acetal. So hemiacetal is converted into acetal. This reaction is similar reaction is taking place in fructose. Actually fructose doesn't have an alcohol group, but it is acting as a hemiacetal and it is giving a fructoside. That means when we take a fructose reaction with methanol in the presence of hydrochloric acid, this methanol is reacting with only 1 mole of methanol. You remember that only 1 mole of methanol is reacting with fructose and giving a fructoside, which is acting like a hemiacetal. So why this is happening? There was a question mark. And this is explained in later by saying that it is not in a straight chain structure, it is in a cyclic strain structure. When it is in a cyclic strain structure, it will have a free OH group like a hemiacetal. That hydroxyl group will involve in methylation and it will act as a hemiacetal. Are you clear? So what is the conclusion we are drawing? Fructose is a ketone group, acts as hemiacetal. Why? It should not act as a hemiacetal, but it is acting as a hemiacetal. This is a drawback in straight line structure of fructose. Let us go into next one. Reduction. Reduction is nothing but we are adding hydrogens. These hydrogens are, if you add limited hydrogens, we will call it as partial reduction. If you add more number of hydrogens, then we will call full reduction. Or we will use a strong reagent of reduction, and here we are using a weak reagent which is giving limited number or less number of hydrogens. So that reagent is sodium amalgam. Sodium is a metal, mercury is a metal, sodium is a soft metal, and mercury is a metal in liquid state. When this sodium and mercury they are merged, you will get an amalgam. This sodium amalgam in presence of water will give hydrogens. Here you can see the structure of fructose. Fructose is having C double bond O. So when this sodium amalgam is supplying hydrogens, this one hydrogen will come and attach to the oxygen, making it OH, and one hydrogen will react with the carbon and it will have a hydrogen like this. So when this hydrogenation is taking place, there are two possibilities. This oxygen can be pushed towards the left hand side or it can remain in the right hand side depending on the reaction. So there are two compounds are formed when sodium amalgam reacts with water. So if you take this hydroxyl group on the right hand side, the total molecule will be same. Only difference you can see at the second carbon. This is first carbon and this is second carbon. In second carbon, when we are reducing this alcohol, this oxygen is becoming alcohol, giving rise to a sorbitol or glucitol. In second case, what is happening? This oxygen is pushed towards the left hand side. Then you will get a different compound. This is called as mannitol. So this is sorbitol, this is mannitol. These two, they are having difference in the second carbon. Everything is same. First carbon to sixth carbon, everything is only difference you can find in the second carbon. When there is a difference in second, third, fourth carbon, we will call these compounds as epimers, and these epimers are generally asked in examination. So what are epimers? Those compounds which are having a difference in spatial arrangement of the atom or stereochemistry. At the second, third, fourth position, these compounds are called as epimers. And if there is a difference in first position, we will call it as anomers. Anomers A, first carbon. Second or third, fourth, we will call it as epimers. You remember that. So sorbitol or glucitol and mannitol, they are epimers. Now let us go into next stage. Full reduction. That means you are giving more hydrogens. Using hydrogen iodide and phosphorus, when this fructose react, all hydrogens will be supplied, and this oxygen and hydrogen, they will get removed as water molecules, and all carbons, they will become saturated and they will give all hydrogens, and you will get a N-hexane. N-hexane means these all hydroxyls and oxygens, they are removed by reduction. So fructose is becoming N-hexane, and this clearly indicates that 6 carbons are in a straight chain. When these 6 carbons are in straight chain, then only you will get a N-hexane, and there is no possibility of getting N-hexane with other type of molecules, because two hydroxyl groups cannot exist on the same carbon. What happens? When the weight is heavy, two hydroxyls, they will give out a water molecule and it will be converted into C double bond O. So each carbon should have a hydroxyl group. So here what is happening? These 6 carbons are in straight chain. We can draw this conclusion. Next, oxidation with bromine water. So bromine and water, it is an oxidizing agent, and this oxidizing agent, it is a weak oxidizing agent, and glucose will be converted into gluconic acid in that case. But in this case, what is happening? You are not getting, it is not getting reacted with the fructose. So bromine water does not react with fructose and it will not oxidize the compound. Next, we will see another weak oxidizing agent, Tollens reagent and Fehling's reagent. Tollens reagent, you can take Ag plus or AgO or AgOH or AgNH3 taken twice OH complex. All this indicates Tollens reagent. In this Tollens reagent, silver is in the silver plus 1 form. The silver will convert into silver and it will give a silver mirror in the reaction. That means the reagent is getting reduced and the compound it is oxidizing. Similarly, in Fehling's reaction, we are having Fehling solution A and Fehling solution B. And in this Fehling solution A and B, what we are taking? In Fehling solution A, you will have copper sulfate, and in Fehling solution B, sodium potassium tartarate is present, and these compounds they will have hydroxyl group. Even in Tollens reagent, you will have base, and in Fehling's reagent also you are having a sodium hydroxide or base. So what is the game here is, while this base is present, this fructose, it should not react with mild oxidizing agent, because glucose is reacting with mild oxidizing agent. But here fructose, it is not reacting with bromine and water, no reaction is occurring. Similarly, it should not react with Tollens reagent and Fehling's reagent, as it is reluctant to have a reaction. But the presence of hydroxyl group will play a key role here. What happens? This fructose, when it is in the presence of hydroxyl group, they will undergo ketoenol tautomerism. You might be remembering that. What is ketoenol tautomerism? This is a ketone group. Okay, you look at here. This is a ketone group, and you are having a hydroxyl group and a methyl group. When this methyl group's hydrogen, it will give the electrons to carbon and these two carbons, and the electrons present in the carbon and oxygen, they will be pushed toward the oxygen, and the hydrogen which is present on the carbon will migrate onto the alcohol and they will give a alcohol. That means a ketone is converted into ene and all. So this ketone is converted into enol is called as ketoenol tautomerism. So when in presence of hydroxyl group or base or alkaline medium, this fructose undergoes a ketoenol tautomerism. When ketoenol tautomerism happens, this second carbon will be converted into alcohol, and first carbon it will have a double bond, or this ene and all are there. This will further undergo the rearrangement or reverse ketoenol tautomerism, and this double bond will migrate towards the hydrogen and oxygen. This hydrogen will migrate to the carbon, and you will get a C double bond OH, which is nothing but a glucose. So what is happening here? Fructose is converted into glucose in presence of hydroxyl ions or alkaline state with ketoenol tautomerism. One direct ketoenol tautomerism and another one is a reverse ketoenol tautomerism. Then you will get a glucose. Along with glucose, this hydroxyl, if it is on the right hand side, you will call it as glucose. If it is good on the right hand side, you will get a manol. You will get two compounds. This rearrangement is called as Lobre-de Boron Van Eknestin transformation. So this transformation is nothing but a rearrangement, where fructose is converted into mannose. As these mannose and glucose are present, they will react with tolerance reagent and failing reagent. Are you clear with now? Fructose is not expected to react with weak oxidizing agent like bromine and water. It will not get reacted. But in case of tolerance and failings, it is getting reacted. What is the reason? The only reason is the presence of alkaline medium. When a hydroxyl group are present, they will go this transformation. When this undergoes a transformation, you will get a glucose and mannose. These glucose and mannose, they will react with tolerance reagent and failing reagent, and they will give a positive reaction. So let us see how this is happening. Tolerance reagent. Just now I told you, silver plus or AgO or AgOH, Ag2O or AgOH or AgNH3 taken plus OH. We can represent tolerance reagent in different ways. The basic logic is Ag2O, it is having oxygen is -2, or you can take as a Ag plus, so tolerance will have Ag plus 1 ions. These Ag plus 1 ions, they will react with the compound and they will oxidize the first carbon into compound, and this group will become a hydroxyl group and silver will be deposited. So you will get a gluconic acid or mannonic acid along with the compound, and the silver will give a silver mirror test. And as this is converting the group, and we will say that the tolerance reagent is reacting here. So fructose is converted into glucose. In this case, as I said, this fructose is converted into glucose and mannose. This glucose and mannose, in presence of base, they will react with tolerance reagent, giving gluconic acid and mannonic acid. And in case of failing reagent, copper plus 2 solution will be there. This copper plus 2 solution we can denote with a Cu plus 2. The Cu plus 2 is in blue color. When it reacts, this blue color will be converted into Cu2O, which is red in color. Looking at the red color, we can conclude that this tolerance reagent and failing reagent, they will react. Even though the ketone, it is having a ketone group, it should not react, but due to this Lobre-de-Baron Van Eckenstein transformation, this rearrangement will facilitate the fructose to convert as glucose and mannose. That's why it is getting reacted. Now let us get into another reaction where oxidation reaction is taking place in fructose. Fructose is reacting with nitric acid, which is a strong oxidizing agent. We have seen a weak oxidizing agent just now. Now let us see if a strong oxidizing agent is present, what will happen. This strong oxidizing agent, they will try to break the bonds. Let us give the numbering. Carbon number 1, 2, 3, 4, 5, 6. This nitric acid is having capacity to break the molecule. Let us see, it can break it in C1, C2. These two compounds, these two carbons, it will break here. We will call it as C1, C2. And if it breaks at C2 and C3, this is C2 and C3, it can break here. Remember a single point that wherever it breaks, the terminal carbons will be converted into COOH. This carbon and these terminal carbons, they will be converted into COOH. Let us imagine it is breaking here. This carbon also will become COOH, and this carbon also will become COOH, and this carbon also becomes COOH. Then you will get a different compound. Let us see the breakage here. That is C2 and C3. This is C2 carbon and C3 carbon. In between these two, if the bond breaks, one compound, this carbon should become COOH, and second, third will have hydroxyl and another COOH. So COOH, OH, OH and COOH. So 1, 2, 3 carbons and 2 COOH will be there. So this is called as tartaric acid. And on the top, what will happen? CH2O is as this CH2OH, and this C double bond will become COOH. So in this case also you will find that a glycolic acid is formed. So this glycolic acid and tartaric acid are the fragments when it is broke in second carbon and third carbon. Similarly, this oxidation can break in first and second carbon. These two are first and second carbon. If it is breaks between first and second carbon, Just I said no, so this will become a carboxylic acid group, and this group also become a carbonic acid. When this become a carboxylic acid, first carbon, second, third, fourth, fifth also carbonic acid. So first is carboxylic acid, second, third, fourth, fifth is carboxylic acid, OH and OH, two OH groups and two OH groups. This is called as dihydroxyglutaric acid. I said that you should remember this dicarboxylic acid using the sentence, oh my such good apple. O means two carbons with two carbons, dicarboxylic acid. That is oxalic acid. My means malonic acid. Oh my such means succinic acid. Oh my such good apples, that means good glutaric acid. These are with 5 compounds, you can say, remember that. Then you will get a formic acid. When this group is converted into COOH, already it is having a hydrogen, so we will be converted into formic acid. So this is the fragmentation. This fragmentation indicates that alpha ketone gets oxidized with nitric acid, not others. So this is a strong point where it says this nitric acid, if the carbonyl keto group is present in third or fourth carbon, this nitric acid cannot make into fragments. Only this fragmentation will be happen when this carbonyl is present alpha position. That is in the second position only when it is there, then only it will give a fragmentation, and we can conclude that fructose is having a alpha ketone. Let us go into next reaction. This can also react with hydrogen cyanide. Here you are having a C double bond O group. In this C double bond O group, there is a chance that this pi bond is very weak bond. These pair of electrons which are present in pi bond, they will be migrated into oxygen. When it migrates towards the oxygen, it will become a negative charge. And here the carbon which is attaching will lose the electron and it will have a C plus. So there is a possibility of carbon becoming plus and oxygen is becoming minus. Here you see the reagent. This reagent is hydrogen cyanide. When hydrogen cyanide is taken, hydrogen will have plus and cyanide will have minus charge. So this hydrogen plus will goes and sits on the oxygen, giving a OH molecule, whereas a cyanide with minus charge, it will go and react with the carbon and giving a cyanide bond. So you can see this second carbon ketone, it is reacting with hydrogen cyanide. One H will attach it to the oxygen and it will convert it into OH group, and Cn minus which will attach to the carbon will give cyanide. So you are simultaneously you are having a cyanide group and also a hydroxyl group. So we will call it as cyanohydrin. This is fructose cyanohydrin. This is actually fructose, but it is having a additional cyano group and hydroxyl group. We will call it as cyanohydrin. So this reaction with cyanohydrin indicates it is having a carbonyl functional group. Maybe it may be a ketone. So that is the conclusion we can draw. Next, hydroxylamine. Hydroxylamine, the formula is NH2OH. This fructose when reacts with hydroxylamine, hydroxyl means OH, amine means NH2. So it should have a NH2 group and hydroxyl group. When this hydroxylamine is attached to fructose, the two hydrogens present in nitrogen will react with carbonyl, oxygen, and they will form a double bond. When it forms a double bond, this hydroxyl will remain as it is, and you will get a new compound which is called as oxime. So when carbonyl group is present, then only this hydroxylamine will react and give a product of oxime. So this chemical reaction also supports that there is a carbonyl group present in fructose. And this is a very, very important reaction. Fructose also reacts with phenylhydrazine, converting this molecule into oxazole. Both glucose and fructose will give same oxazole. That we try to remember. The only difference is here in case of fructose, this phenylhydrazine, which is C6H5NH NH2, will react with the second carbon, that is ketone carbon of the fructose, and these two hydrogen and oxygen, they will come out as water, and this nitrogen will be attached to the carbon, giving C double bond N NH C6H5. Okay, this is the phenylhydrazone. Phenylhydrazone is formed. When phenylhydrazone is formed, now comes into second second molecule comes into the picture. In the same case, what will happen? Here in case of this hydrogen and hydrogens are removed. So similarly, now this phenyl hydrogen will remove 2 hydrogens from first carbon. When it removes 2 hydrogens, one molecule will be converted into ammonia, another will be becoming into a aniline, and this carbon will become C double bond O, which is the aldehyde group. So again, this CH2 is converted into aldehyde. This is nothing but oxidation or removal of hydrogen, and second molecule is consumed to make this carbon oxidized or converted into aldehyde or carbonyl function. Now, third molecule of phenyl hydrazine will react with this, and 2 hydrogens and oxygen, they will go out as water, and this nitrogen will be attaching to the carbon, giving NHC6H5. Like this, same ozone is coming from glucose and fructose. The only difference is 3 molecules are consumed here, 3 molecules are consumed. The difference is in steps. So first, what is happening? In place of glucose, first carbon is reacting and second carbon is getting oxidized in second step. In third step, ozone formation taking place. Whereas in case of fructose, first it is reacting with second carbon, and in second step it is oxidizing first carbon, and this ozone formation is taking place in third step. So in examination, they may ask a long question that glucose and fructose will give same ozone with phenyl hydrazine. Explain why and give the reaction. So in such case, you are supposed to write this reaction. Now let us go into next reaction. Cyclic structure. Glucose will be in the cyclic structure, and mostly it prefers to stay in 6-membered ring. But when it comes to fructose can stay in 5-membered ring and 6-membered ring both. How it is forming a 5-membered ring and 6-membered ring? Let us see. Let us see the numbering first. First carbon, second carbon, third carbon, fourth carbon, fifth carbon, sixth carbon. This is second carbon. This second carbon can get connected with the fifth carbon. When it gets connected with fifth carbon, 1, 2, 3, 4 carbons will be there. This oxygen will come into link. So you will have total 5-membered ring. That means 4 carbons and 1 oxygen, which is something like furanose. Something like furanose, we will call it as furanose, fructofuranose structure. And in formation bond, when bond formation takes place in second carbon, this oxygen can remain on the right hand side. If it remains on the right hand side, it will goes down, we will call it as alpha. And it can be pushed towards the left hand side. When it pushes towards the left hand side, it will come on the top, we will call it as beta. So when a cyclization takes place, within the molecule, intramolecular cyclization takes place, you will get 2 compounds. One is alpha and one is beta. These 2 compounds are different in optical activity, and these are called as optical isomers. So fructose will have isomers, like you remember alpha D fructose and beta D fructose. Or if you want to say more clearly, why we are calling alpha? This group alcohol, when it is becoming second carbon is becoming OH, it will be on the right side. When it is on the right side, it will come toward the downwards. When it is on the left side, it will go to on the top. So we will call it alpha D fructofuranose. It is by furan, it is something like furan. You can remember oxygen and 4 carbons with double bond, we will call it as furan. So as it is something like furan, so we will call it as furanose. So this is beta D fructofuranose. Now let us see how the 5-membered ring and 6-membered formation is taking place. Just now I have explained about the 5-membered. So glucose, it is having second carbon, you can see a green coloration, okay, and second, this is burst, second, third, fourth, fifth carbon's hydroxyl I have given with a blue coloration. Sixth carbon's CH2O group is in red color, and first carbon's primary alcohol is in CH2OH. I am holding black CH2OH like this and red CH2OH like this. Slowly I am turning towards upside down. Then what will happen? Automatically the groups which are present on the right side will go towards the down, and the groups which are present on the left hand side will come on the top. So these groups will turn like this. So in that case, what is happening? This CH2O group you can see here, the CH2O group with black, and this oxygen is going down, and hydroxyl it is coming up. This hydroxyl which is on the right hand side will go down, and this hydroxyl is going towards to react with the carbon, and in transformation this CH2 group will come on the top. Now what happens? Second carbon is reacting with fifth carbon's hydroxyl. Second carbon, this is first carbon, second, third, fourth, fifth. So second carbon's oxygen is reacting fifth carbon's hydroxyl. The pair of electron is donated to the carbon, and the pi bond electrons will migrate towards the oxygen, and there is a bond formation between oxygen and carbon, and hydrogen will be removed. That hydrogen will come and sit here. Then you will get a bond between this oxygen and carbon, which is a new bond formation with a blue color oxygen you can see, and this oxygen it is having a hydrogen, green color oxygen and blue color hydroxyl. You are getting a 5-membered ring, and this is furanose, fructofuranose, alpha D fructofuranose. Alpha means the hydroxyl is on the right hand side and it is going down, this is alpha. D means the blue hydroxyl on the right hand side, we will call it as capital D. Fructose, it is nothing but a fructose. Furanose means it is 5-membered ring, it is called as furanose. Similarly, you can also find 6-membered ring, which is called as pyron. 5 carbons and 1 oxygen is present, we will call it as pyranose. So let us see how a 6-membered ring is formed. Same story. Here, first carbon, second carbon, third carbon, fourth carbon, fifth carbon, sixth carbon. Again, I am holding the CH2 red black molecule and CH2OH red molecule. I am turning to vertical to horizontal. When I am turning to vertical to horizontal, the groups present on the right side, let us say these are right side, this right side groups, they will go down. And whatever groups are present on the left side, they will go on the top. Simply turn the molecule like this. So here you can see this CH2O group is here, and this oxygen is coming in this side, and OH is going on the top. This OH is here, and OH is, this should be a blue coloration. This OH is here. And now the second carbon's oxygen is reacting sixth carbon's oxygen. 1, 2, 3, 4, 5, 6. This is 1, 2, 3, 4, 5, 6. So 6 carbons oxygen will donate electrons to the carbon, and the pi bond electrons will migrate towards the oxygen, and the hydrogen will come and sit on the oxygen. You will get a 6-membered ring. This 6-membered ring, you will have 1 oxygen, 1, 2, 3, 4, 5 carbons. This is first carbon, this carbon, and second carbon is having OH, C double bond O, that is converted into hydroxyl, and you will have rest of the carbons, and this oxygen is coming into this position. So this is nothing but alpha D fructopyranose. If the hydroxyl group is on the top, we will call it as beta. If it is on the low, we will call it as alpha. Okay, how we are deciding it? When the cyclic structure is there, then you will get this hydroxyl group on the right hand side, they will call it as alpha. If this oxygen, if it pushes towards the left hand side, then they will become alpha. So in this case also, in fructofuranose also you will have alpha beta, and in case of fructopyranose also you will have alpha and beta. So glucose can exist only in 6-membered ring, whereas fructose, depending upon the situation, in some cases it will be as a 5-membered ring, and in some cases it will be as a 6-membered ring.